Let's start by understanding the project's overall architecture and how files are organized. Looking at the system's architecture, we have a hierarchical structure with clear separation of concerns. At the top level sits the real controller, which acts as the brain of our network. The controller maintains a global view of the network topology, makes routing decisions, and manages the behavior of all switches. It's the central point of intelligence in our SDN architecture. Below the controller, we have the mini network, which consists of virtual switches and hosts. Mininet creates a realistic network environment by using lightweight virtualization. Each switch runs an instance of Open vSwitch, and each host behaves like a Linux machine with its own network stack. The switches and hosts are interconnected with virtual Ethernet links, creating whatever topology we specify in our Python scripts. Communication between the controller and the switches happens through the OpenFlow protocol. OpenFlow defines a standardized set of messages that allow the controller to discover switches, query their capabilities, install forwarding rules, and receive notifications about network events. This protocol abstraction is what makes SDN possible. Turning to the file structure, the project is organized into several logical directories. The startup scripts directory contains 3 key files. The start SDN demo.shell file script is for Linux and Ubuntu users who want to run natively on their host system. The start SDN docker.shell file is for Windows users running in a Docker environment. The controller logic directory contains our most important file, main controller stp.py. This file implements the complete controller application. It includes STP loop prevention logic to avoid broadcast storms and does all OpenFlow message processing, including switch connections and packet in events, implements the Dijkstra's shortest path algorithm for route computation. The network topologies directory contains the Python scripts that define different network configurations. The ring topology.py script creates a 10-switch ring structure, which is what we use for the main demonstration. The configuration directory contains requirements.txt, which lists all Python package dependencies with their exact versions. Finally, there's a comprehensive documentation file which provides detailed explanations, troubleshooting tips, and additional experimental ideas. Now let's discuss the first of 2 crucial protocols, LDP, or Link Layer Discovery Protocol. LDP is an IEEE standard protocol. I want to emphasize something important here. LDP is not unique to SDN or OpenFlow networks. It's a general purpose layer 2 protocol that has been used in traditional networking for many years. The fundamental purpose of LDP is to enable network devices to automatically discover their neighbors and understand how they are interconnected. Without LDP, a network administrator would need to manually document and configure which switch port connects to which other switch. This manual process is error-prone and doesn't scale well to large networks. Let me walk you through how LDP Discover works in our SDN context, referring to the diagram on the slide. In the first step, the controller generates the LDP packets and sends them out through the switches. The controller crafts special LDP frames containing information about the switch and port from which they are being sent. It then uses OpenFlow packet out messages to inject these LDP frames into each port of every switch in the network. In the second step, neighboring switches receive these LDP packets on their ports. When switch 2's port 1 receives an LDP packet that originated from switch 1's port 3, switch 2 recognizes this as an LDP frame and sends it to the controller using an open flow packet. The packet encapsulates the LDP frame so the controller can examine its contents. In the third step, the controller processes this packet and extracts the valuable topology information. By analyzing which switch and port sent the LDP frame originally and which switch and port received it, the controller can deduce the switch 1's port 3 is directly connected to switch 2's port 1. In the fourth step, this entire process repeats periodically. Typically, LDP packets are sent every 5 to 30 seconds, depending on the configuration. The reason LDP is so critical in SDN is that the controller's power comes from its global view of the network. If the controller doesn't know which switches are connected to which other switches, it can't make intelligent routing decisions. LDP provides this essential topology information automatically and reliably. The second critical protocol we need to understand is STP, the Spanning Tree Protocol. Similar to LDP, STP is an IEEE specific standard, specifically IEEE 802, and it's not specific to SDN. STP has been a fundamental part of Ethernet networking for decades. The purpose of STP is to prevent that we call broadcast storms. Look at the left diagram, which shows 4 switches connected in a ring topology. This creates a loop in the physical topology. Now imagine that host A sends a broadcast packet, perhaps an ARP request trying to find another host's MAC address. Switch A receives the broadcast and following standard Ethernet behavior, forwards it out all its ports except the port where it arrived. So the broadcast goes to both switches D and B. Now, both of those switches receive the broadcast and forward it to the neighbor switch D, forwards it to C, and switch B also forwards it to C. Meanwhile, switch C forwards the packet to D and B. The packets keep circulating endlessly around the ring. STP solves this problem with an elegant solution. STP identifies the loops in the topology and selectively blocks certain links to break their loops. With that one link blocked, the topology is transformed from a ring into a tree structure. Now, when a broadcast packet arrives, it propagates through the network but doesn't loop back on itself. In SDN environments, we have an opportunity to implement STP more efficiently because the controller has a complete centralized view of the topology. It can identify loops instantly by analyzing the topology graph. Now, I'm going to open the actual controller code and walk through the key implementation details. Let me open main controller stp.py first. This is the heart of our SDN controller. Firstly, let me highlight the important imports. We import the base view app class from the view base app manager. which provides the framework for building controller applications. We import various OpenFlow event classes like event OFP switch features, event OFP packet in, and event OFP port status. These events are triggered when switch is connected, when packets arrive at the controller, and when port states change. For topology discovery, we import the topology modules event switches from Vue topology. These handle LDP-based topology discovery automatically. Most importantly, we import network X, which gives us the graph library we use for Dijkstra algorithm. So here we define our main controller class, which inherits from Vue app. This inheritance gives us access to all the Vue framework functionally. In the initialization method, we set up several critical data structures like data paths or host locations or topology graph. Notice we use DEC over here for the broadcast cache. This automatically removes all old entries as new ones are added, preventing memory issues. Here's the first important event handler, switch features handler. This function is decorated with set EV class, which registers it to handle event OFP switch features, events with config dispatcher priority. This event fires when a switch first connects to the controller and sends its capabilities. Inside this handler, we extract the data path and we store it into the self.data paths. We clear any existing flows and we install the default table misflow and we trigger topology discovery. Let's see each function's details step by step. Install table misflow function show you how we construct an OpenFlow message. So firstly we create a match object specifying which packets this rule applies to. And then we define an action list. And we call add flow with priority 0. So this only matches if no other flow matches. This is a crucial rule. Without it, packets that don't match installed flows would simply be dropped by the switches. Here's where STP implementation happens. The compute as spanning tree function firstly uses network access minimum spanning tree function to compute the minimum spanning tree using our topology graph, finds the difference between all edges and tree edges, and for each non-tree edge, we identify the port that should be blocked and add it to self-blocked ports. In our ring topology, this algorithm detects that one link needs to be blocked to break the loop. The discover topology function is called whenever the topology changes. Here's what it does. So firstly, it queries the real topology module using getSwitch to get all switches, and then get all links using getLink, and clears and rebuilds our network X graph, and then adds each switch as a node in the graph. Iterates through links, adding edges with weight 1, and storing port mappings. And lastly, calls compute spanning tree if we have at least 2 switches. This graph structure is what enables us to use network access graph algorithms, including Dijkstra. Here's the function that calculates the shortest path. This function takes a source switch ID and destination switch ID and computes the shortest path between them. We firstly call shortest path function in the network X library. Once we have the path, we install flow rules using install path flow. Firstly, this function creates a match condition for the specific source and destination MAC address. And then define an action to output and calculated port. And lastly, install the flow with priority 10, timeout of 10 seconds. The 10 seconds timeout is important. When a link fails, these flows expire quickly, forcing the controller to recalculate paths with the new topology. The packet in handler is the most frequently called function. This event fires whenever a switch receives a packet that doesn't match any existing flow entry. So let me summarize the complete flow. Firstly, the switch receives the packet, and then controller examines packet, and then the controller check the STP. If it is just checking if the port is blocked, and then if the broadcast happens, check for the duplicate, then flood using STP allowed ports only. And if unicast and destination known, calculate the shortest path using Dijkstra. And then install flow entries on the switch, forward this packet immediately, and then future packets match the installed flow. This reactive approach scales well because we only install flows for active traffic patterns, and our STP broadcast detection prevents storms even before flows are installed. And let's see the ring topology file. Over here, we add 10 switches and one host for each switch. Hosts are always connected to port 1 of their switch. And over here, with the for loop, we are creating the ring structure. Each switch uses port 2 and 3 to connect with neighboring switches. The last switch connects back to the first switch, S1. So it looks like this.